Hi. So, long time no see. It's been almost 2 months that I recorded something. So, I think it's high time now. So, yeah, I don't know, I was out of touch with theoretical parts of computer science. I had stopped reading books. So, yeah, so I was having this discussion today with a friend that how mm, these AI coding tools are making you more productive, but they're also stripping you of your intelligence and your basic thinking power. So yeah, after talking to him, I realized that maybe that's what I've been doing for the past 2 months. That I've been just talking to Claude and ChatGPT and just extracting code out of them rather than actually applying my brain. Um, I don't know how much of a issue that would be in a long term, but I think we all need to be careful actually. We all need to be careful about how we are, like, we need to use our brain cells or our brain is just gonna go dumb. So yeah, I have also thought that starting from today, I'm gonna get back to these videos. Plus, I'm going to start solving some lead code, just to just as a good practice measure. And I'm going to solve lead code with no connection, no internet connection. I might stream it. I might solve like I might do a sprint of 5 questions, which I would like to solve in 30 minutes ideally. So I might stream those 30 minutes. Not that I expect anybody to watch, but I might stream that. So yeah, let's see how it pans out. But yeah, I'm more inclined towards using AI as a tool that just gets stuff quickly done. But when it comes to uh, anything that I'm doing as a hobby that is like just for self-learning, I have decided that I would use the AI to a minimal level. Like I would just go back to the old school technique of skimming through books and making notes on preferably notebooks because I was making notes on the tablet itself, and I realized that making notes digitally is not as, I know it doesn't make sense, but making notes digitally is quite different to making notes physically on a notebook. Yeah, this usually doesn't make sense. It's a me thing. But anyways, a lot of talking. And, okay, so let's start with that. We were discussing about buffer pools. So what are buffer pools? We were discussing that databases are just files on disk, and when you need to read those files, you bring them into memory, into your main RAM. And where do you hold them in your main memory? That is a dedicated space that you have in your main memory. That's called the buffer pool. So you have limited physical memory. So that implies that you have a limited buffer pool. So when you have a thing, limited space, what you want to do is you want to swap things. That you want to swap pages which are not heavily used, and you want to keep the pages which are hot and are frequently used. So we discussed a lot of algorithms that we discussed at FIFO, we discussed FIFO, and we discussed last in first, no, uh, LRU we discussed, and then we discussed LRUK. Then we discussed a new technique called ARC, that is adaptive replacement cache, that maintains two queues of one giving you the sense of frequency and another giving you a sense of recency. So you maintain a parameter p, which adjusts and which just gives you some idea as to where a new page should go. Should it go into the recency list or it should go in the frequency list? So, anyways, after that, we saw that there are some better policies like priority hints, like you might want to keep the root page of a B tree in memory. Then you have something known as dirty pages, that when you touch a page, then how do you want to write it back out to the disk? Do you want to implement a steel force policy, a no steel, no force policy, and a no steel force policy, or you might do the cross of that steel and no force? So what is steel? Steel is something that um, steel is something that so you're writing into let's say you touched a page in buffer pool, and what you do is in an active transaction you steal that page and you write it out to the disk, not caring for the not caring that how it might be might affect the actual pages on the disk. So you just do you pick the page, you steal the page from the transaction, and you write it out. What is force? Force is that when a transaction commits, as soon as it commits, you flush all the pages, and until all the pages are flushed, you don't acknowledge a commit back to the user. So what that might cause that if you're using a forcing technique, that might slow down your system because now you are flushing pages out on every commit message. So there might be contention on the disk writer itself, but there might also be contention in the version writing of the system of a tuple in a particular page. So a lot of things might be holding locks to that particular page. So what ideally you want to implement is you want to implement a no force and along with a steal. So what would you wait a second. Ideally you would do a no force and a steal. Let's see why. No force says that what does a no force say? No force says that on every commit, it is not necessary for me to flush out all the pages. Yeah, that's the ideal scenario. So yeah, I want a no force. So no force is a good parameter. Do I want steal or no steal? Okay, so can the background writer pick a random page and write it out to the disk? Hmm. Well, you might want to do some trade-offs on that too, because I can think of scenarios where steal would be helpful and where no steal would be helpful. So I wonder what Aries is. Have you heard about this algorithm called Aries? I think Aries is a no force algorithm. So Aries is hmm, yes, it is a steal algorithm actually. Oh yeah, that's okay. I'm dumb. See, it has to be a steal algorithm, right? Because Aries uses the write ahead log. So whatever a transaction does, you record it in a write ahead log. So you write that in, and if you are even writing the page out in the middle of a transaction, you don't need to worry about it because if if a transaction gets aborted, then you have the log with you, so you can replay the log and do the undo the changes from the page itself. So yeah, Aries is a steal and no force, which most of the I think most of the background writers will implement. So yeah, background background writing, we discussed that how a separate thread is picking up pages from the buffer pool and writing them out to their respective location on the disk. Okay, so I think we were going to start with disk scheduling. Yeah, so let's start with disk scheduling. So I have not been in touch with database systems for quite a time now. Like it's been 2 months since my last video, and I really need to get back to the books. But anyways, consistency. Damn. Okay. So let's talk about IO scheduling. So as you know, what you need to do with buffer pool pages, you need to write them out to the disk, and you also need to read pages out from the disk to the buffer pool. So if you're doing schedule based IOs, then you might be able to efficiently pack together input output operations which are close together. So back in the days when we used to had spinning disk hard drives, if you have if you are reading bytes consecutively, that would be much faster than reading bytes at random offsets. So that still applies, not so much with the new SSDs, but if you're running solid disk drives, sorry, hard drives, the physical, like the one with spindle and plates. So in those, these principles might still be applicable. That if you have bunch of blocks that are to be read from the disk, if they're close by, then you might be able to read them at a faster rate. So you might want to reorder your input output operations depending on the locations of the data that you're requesting. So as the slide says, you have various compute priorities. So depending on either it is a sequential access that the blocks are lying close together, or it's a random IO that the blocks are lying at random locations. Depending on those factors, you might want to reschedule your IO requests. Then you have the read path that you are dealing with. So there might be that a particular operation requires immediate flush to disk, like an fsync. So what an fsync would do is that you are asking the hardware to just bypass all the scheduling and just write your page immediately out to the disk and give you an acknowledgement back. If you're doing a background task, then you might be lenient on that particular scenario, that you might not want an immediate response, that you don't want to flush it out immediately. But yeah, you just make a write request, and the write request just lingers on there until a lot of write requests come in, and the scheduler then decides that yeah, it's time to write them out to the disk. It also depends on the factor that what data structure you're dealing with. So either you're dealing with tables, or you're dealing with indexes, or you might be dealing with the log itself, or ephemeral data. I wonder what that is though. So anyway, I do see that how the data structure itself might affect your IO schedule, because assume you're writing an index, right? So you're writing a B tree. So if you're writing a lot of pages, and the pages are let's say you're branching out the tree, and the children are the pages, right? So if you are making pages, they might be lying across the disk. So if you're writing a B tree, you're doing a bulk load, and you're writing a B tree from scratch. So what will happen is that you're doing a lot of random writes, because you might be able to allocate the B trees consecutively, but as you insert data into the B tree, you tend to move the nodes of the B tree far apart on the physical disk itself. So yeah, that would result in non-sequential IO. So yeah, your writes to those might get scheduled and not be immediately written out to the disk. Okay, so if we, I do wonder what this data is. I'll have to study about this. I don't know how transaction information and user-based SLAs deal with this. I'll have to read about that too. So yeah, OS does not know these things and is going to get in the way of our beautiful DPMS. So yeah, all the listed above, like the data structures, the tables, the indexes, then either you're hitting a critical path, or a background task is doing the write, which is not a critical path, and uh, you are loading bulk loading a index, or you are just loading a data like a table. So all those things the OS is not aware of because these are high level structures which the database software is aware of, that it knows that what it's dealing with. But to the OS, our read and write requests are nothing but just read and write requests that some other random program would issue to it. So yeah, the OS page cache. Let's talk about that also. So there is one database system. I do remember this line very particularly from the lectures that Postgres relies heavily on the OS page cache. So other systems will tell you that while setting up the system, allocate 80% of the memory to the buffer pool and 20% to the OS page cache. But Postgres will tell you that allocate 80% of the memory to the page cache and use 20% for the buffer pool because it's heavily relying on the OS page cache. Now, what is OS page cache? Um, so let's say you load in a file. So file is loaded in. Now the OS will cache that particular file in its own user segment, not the user segment, like the kernel segment. Any kernel space that it finds, it will try to cache that particular page, unless you run out of the cache space and then you need swapping out on the cache level too. So yeah, most DBMSs, they what do? They use the ODirect flag. When you use a ODirect flag, you instruct the operating system that you don't want to use the OS page cache because it might cause some synchronization issues that some version of the file is lying on the disk, but the OS page cache is inconsistent with that version. So you might be reading some inconsistent data. So some DBMSs might have problem with that because you can clearly see how that would be a problem, right? If you're reading stale data from the cache itself, but some background writer has made change on the disk itself, and you're still being served from the OS page cache. But according to you, like as a user, what you have done, you have just issued a fread. You've issued a read system call. So to you, it is reading from the OS page cache is equivalent to actually reading from the disk. So most database systems, they will just use the OLED flag that you don't want to deal with the OS page cache because you don't want those inconsistencies that you're reading something from the OS page cache and the actual data is something else on the disk. So yeah, this is some talk about this. So yeah, what OS page cache does is, so yeah, as I was saying, that you're just issuing a read system call, and according to you, you are directly reading from the disk, but you might get served from the OS page cache itself. So what ODirect does is it bypasses this particular system and just goes straight out to the disk. Of course, there might be uh, the operating system has the cache in place for a reason that you might be able to serve some request faster. But when you're dealing with systems like a database management system, which handles transactions with like system critical data and like mission critical data, then you don't want those consistencies. Like you might, it's again about the trade-offs, right? Like if I'm writing a random program on my system, which I don't care a lot about, then I'm fine using the OS page cache. That if I'm just reading stale bytes, then yeah, I would be fine if I close off the system and I discover that there is some inconsistency in the program. But when users are trusting you with their data, that your software is good enough to handle their transactions, to handle their users, then you cannot leave any ambiguity in the system itself. So yeah, that's a good word actually, ambiguity. The ODirect flag, sorry, not using the ODirect flag introduces ambiguity in the system. So yes, so we talked about fsync last time also, I think. But anyways, what fsync was, fsync is a system call that you place to immediately flush out any data to the disk. So let's say you have touched the page and the transaction says commit. So on that commit, assume that you are using a force policy. What you would do is you would take that page and you would immediately flush it out to the disk. How would you flush it out and guarantee that it lands on the disk? You use a blocking call called fsync. So when your program calls fsync, it blocks and it waits till that fsync completes. And what fsync does, it just writes it out to the disk and returns when that particular call is finished. So there was this fsync error in which was discovered in 2018, I think, that was called fsync gate. So what happened was you called fsync. So a lot of database systems they used to call fsync in a loop that you fsync and if you fail, then you again call fsync because you're writing it out, right? So what the Linux kernel would do is first time you do fsync, you fail, but uh, your page is not flushed out to the disk. But the next time you come around, you do an fsync. The OS tells you that your fsync succeeded, but in the actual reality, it did not. But because what happened in the first fsync, it marked your dirty pages as clean. So according to the OS, nothing is touched. Although nothing is written out to the disk, but it marked the dirty pages as clean. So according to the OS, you did not touch anything, so your fsync just returns successfully. Why this was done? So this was, as far as I remember from the lectures, that somebody in the kernel, like some of the maintainers, they were worried that somebody would plug in a USB thumb drive, and as they are reading from the thumb drive, they would load in a lot of pages, and they would plug it back out, and there would be a bunch of pages that would just be lying around in the cache and then in the RAM. So you might not be able to flush them out because they are dirtied, and but the USB thumb drive has been plugged out, so they will never be used. So yeah, but I still have to dig deep into that though, why that happened. So yeah, this was the post on the Postgres forum that some guy lost some data and uh, he reported it on the Postgres mailing list, and then somebody dug into that and actually found that fsync was lying to you. So yeah, wait, did we? Oh no, I think we covered this last time. No, screen sharing. I think we covered this last time. Oh no, just a second. Did I just time is not wasted, but still. No. Okay. So did we did not record this. I do remember recording this, but I did not put it out, I think. But I see that I posted the last video 2 months ago. Then I posted it 3 months ago. That's inconsistency at its peak. Anyways, so we'll be quick with this because I just want to put a video out, just get this thing going, that this slack that I'm having of putting out stuff and working on myself. So I just want to put this particular video out as fast as possible. And also I want to get over with buffer pools because it's been 4 months that I have been doing buffer pools now. Anyways, I hope my audio is being recorded. Anyways, so there are some buffer pool optimizations that we can talk about. So the slides are pretty clear though. So what you can do is you can have multiple buffer pools. You can have per table buffer pools, you can have per database buffer pools, you can have per page type buffer pools. So depending on how complex your system is, you can have a lot of bells and whistles, and you can enable users to use multiple levels of buffer pools. So the enterprise systems like the Oracles and the SQL servers, they would have more variety of buffer pools in their system because they are enterprise and that's what you pay for. And but the open source systems like Postgres and MySQL, they would just have some common buffer pools. They might have some additional, like Postgres has this circular ring buffer, which it uses for sequential page scans. But yeah, the enterprise systems, they will have a lot of other types of buffer pools in their system. So this slide shows that you have different buffer pools. So what you can do is you can hash a particular field or a key, and you can check that which buffer pool should I put it into. So let's say you have an object identifier, which can be the primary key, or it can be the synthetic primary key that you generate. Uh, so a primary key can be logical itself. Like something you specify that this is a primary key, like your email or your phone number, or it can be database generated. Like you can identify a particular row by its location, but the database system itself can also generate an internal ID just to just for better bookkeeping. Sorry. So So you might want to use a primary key. So in this example, the just for demonstration purposes, we have used the object ID, the page ID, and the slot number in the page ID. We can combine those three, hash them, and then figure out that which particular buffer pool I want to go into. So okay, so we are not hashing the object ID. We are just saying that this particular object ID belongs to this buffer pool. But another good measure would be hashing, because you have n number of buffer pools, and if you want to oscillate between them, then what you do, you use the modulus function. And a modulus function will always be I want to say commutative, but that's not commutative. When the thing is complete, what do you call that property? Not a modulus actually, mod function. Still reading modulus. Hmm. Array abstract algebra. In abstract algebra used to be one of the beautiful subject I had, like one of the best subjects that I had in my mathematics course. I loved proving that some group was, they had a different properties that if you have a group and you define, not a group actually, if you have a number of elements and you define some operation on that, it could be abstract operation. So not necessarily that you are given number of integers, and the question might say that the plus sign is not the addition, the traditional addition, but it's something else that it might be multiplication. Then you had to prove a bunch of properties that the particular thing forms a group. Now, what is a group? Group might have used to have this bunch of properties. So they were like predefined. I think they used to call them axioms. So something that you just assume that is true. So you take that as your building block, as your basic. and you start proving that that particular system formed a group. And once you prove that that particular thing is a group, then my battery is about to die. Anyways, wait, let me get the charger. So once you define that, once you prove that a particular set of elements is a group, then you could use that particular group of elements to do a bunch of operations. Like, I think the real numbers, they form a group. No, all the integers, they form a group under addition. So if you define the operation addition, the standard addition on all the integers, that is negative, zero, and the positive integer, then they form a group. So you can always guarantee that the addition of the two, like addition of two integers, will always lie in that, will be an integer. So yeah, that was very abstract. So some like at the beginning, used to ask, this is so useless. Like, why would you prove that sum of integers will be an integer? But then I realized that, if you prove that, then you can just use that particular concept and you can extend it out to abstract elements. So, where was the application? I from the group. I had some application I was very fascinated about. It was, I think, in my physics class that something physical, uh, not something physical, I think, but something formed a group. Something formed a group, and then you could use all the properties of group, and then you used to use that to prove some theorem, which just blew my mind away. And then I was just had respect plus plus for my mathematics professor. I'm like, teach me abstract algebra, please. Anyways, uh, what was I discussing? What was I discussing? What was I discussing? What? Okay. Um, Group closed, I think, is mod function closed. Yes, the property I'm looking for is closed. So if I'm defining this mod operation, what it says that the result that I get will always be from 0 to n. So after n, it just cycles back to 0. Anyways, mathematics. I should start a mathematics series also. Anyway, so what you can do is you can use the primary key or the collection of some logical keys, and you can combine those keys and hash them, and you can find a buffer pool that you want to put the record into. What another thing you can do is you can prefetch. So let's say you're traversing an index, a B tree, and you know that after root, you are either going to go left or right. So what you can do is if your system is idle and you don't have a lot of traffic, you can prefetch those two pages. So I might want to jump to the right, but I will already have it in the memory. So I won't have to issue and wait for a IO request to complete. So like page 0 is loaded in. So if I'm doing a sequential scan, then the scan can actually figure out that what next page I'm going to read. So I'm going to load that particular page in. So assume that page 0 is read. So my system can figure out that next I'm going to read page 1. So it can load page 1 in ahead of time. So as we go, we do page 2 and then we do a replacement algorithm and we replace page 0 with page 3 and so on. Yeah, so so this is for index pages that depending on what your query wants to do, you might want to fetch index pages too. Now that I've thought about the the kind of mathematics that I had to deal with in college. Uh, this database stuff actually seems easier, dude. But my teachers were lenient. They were like, uh, the college itself was lenient. They didn't have a lot of restrictions. So you might just want to, they weren't strict on attendance too. So like I could wander off to the library or to my workplace. So I was interning at that time. So I could wander off and do my own stuff while as long as I passed the exams and as long as I performed in the tests. Not a lot of people cared. So like some professors cared, like my physics professor, he wanted 75, 80% of attendance. So he used to maintain that register and he used to call out names that is this roll number present or not. I used to dread that class though because I don't know that you know I had good teachers. I don't want to say something about the teachers, but yeah, yeah. Anyways, so index page zero is loaded in. Then depending on what structure you are, what logical structure you are dealing with on the index, you might want to go left or right. But if you're dealing with a a hash index, then you might want to just jump off to some other location. But you might be able to do prefetching on that too. So yeah, this is a this is a demonstration actually. So index page is here, so page zero, and you're doing a query which says value between 100 and 250. So 100 and 250. So you need to find these two edges. So you just need to find one edge, and then you can traverse to the right because we don't have a 250 edge. So what do you want to do? You want to read this page in. That's what the next slide will do. Read this page in. Now the query can figure out that depending on the split, I want to find 100, right? So what I'll do is I'll go to the left. So most preferably, I'll want this page one to be on my next slot. So my page one will be in the next slot. But now look very carefully. Now, depending on this page, I want to go right because some key in this particular page tells me that 100 will be lying to the right of my or to my right child. So what I want to do, I want to index page 3. So I might want to prefetch this. So I don't want to prefetch page 2. I might want to prefetch page 3. But you can write a smart software and uh, and which might be able to figure out that you're going to do a range scan. So what you can do is if you look carefully, this is just a linked list at the bottom and you're building a scaffolding on top of it. So if you have a smart system, it can figure out that you want to traverse the whole of the linked list and it can prefetch the next page too. So when I say smart system, I don't mean like actually a smart system, but it's a heuristic based system. But you might be able to do some tricks with the heuristic based system too. So scan sharing is simple that two queries show up, and if they want to read data from same pages, then you bring in pages from for one request, and then you piggyback the second query on top of that first query. So both the queries can read from the same pages as long as no query is modifying the page. So when you are writing to a page, then you might want to hold a lock, exclusive lock to that, so that nobody can read the database in an inconsistent state. Like if query one is moving stuff around in the page, you don't want query two to look into it because at that particular point you might be reading corrupted data because query one is still in progress. So that's a classic concurrency problem for you. So, Oracle supports cursor queries sharing for identical queries. So the string of the queries has to be similar. So, like if you look at this, this is from Oracle Docs. So these, since the sorry, this is the difference, and this particular space is difference. So what you can see is from the first query, the second one differs on that capital E, and the third one differs on that extra space. But to the Oracle system, it will look like that these are three different queries. They although they are going to logically touch the same pages and physically touch the same pages, but uh, to the Oracle parser, it looks like these are three different queries. So they are not they cannot do that scan sharing thing. So I think that is what, as far as I remember. Hold on. For a textual match over for example, the following state. Oops. Wait, did I just? Oh, this is tappable. Let me close other tabs, by the way. Let it open. Oh, yes, I can do this. I wonder where. Okay, so this is that particular thing. For example, the following statements cannot be used to use the same shared SQL area. Why? Because they are actually the string of the query is not equal. I didn't know I could just tap on that though. Anyways, scan sharing, this is a physical representation, like a visual representation for you, that some query shows up. It wants to aggregation on the table A, and it wants to sequentially scan all the pages. Now, during this course, let's say it has completed till page 2, another query shows up. Where is the second query? This. It wants to compute an average. So what I can do is, uh, apart from like instead of starting from page 0, I can piggyback query 2 on top of Q1. It can scan along with Q1. So Q2 will not start from here. It will start with Q1. So now you can see that Q2 is on top of Q1. So they both are reading from the same space. And when they reach the end, Q1 is done because it started from the top. But Q2 has some partial data, but it can go back and read the remaining pages. But what was the benefit of this? That you didn't have to do two different reads for the same pages. Problems would occur when one query is writing also. So yeah, scan sharing is just strictly for read only. So these two slides are showing that for the remaining pages, Q2 is going ahead and reading the remaining pages that it missed. So limit 100, limit 100. I don't know why that statement is there, but I think what it demonstrates is that if you're doing a limit 100, then limit 100 does not specify that you want to start on top of the database or not. So if you are piggybacking off of Q1 from here, then you might be able to just read 100 tuples in that span of space, and you might not want to go back to page 0, 1, and 2. So there's something known as a buffer pool bypass, which I might want to read through before explaining. Okay, so this is talking about a private buffer pool for queries. So like in Postgres, we have those sequential buffers, not sequential buffers, sorry, circular buffer for sequential queries uh, for each query. Then, and this is also talking about the same thing, that each query has own specific private buffer pool, which it might want to use for temporary data, like for joins or for sorting. Uh, yeah, I think that's what it's saying. I think. Anyways, I'm very done with buffer pool at this point because I've been extending these particular slides. How many there were? 47? No, wait, there were 130 slides. Why is it named 47? 45, 44, 44, 44, 44. Okay. This particular number is wrong, I think. So there were 344. So yeah, that explains this. So what we will do is we will give up on buffer pools now. No more talks on buffer pools or replacement algorithms. Maybe in future. But next class we will jump back to cool things like storage structures. That when you're laying your database out to the disk, that what logical structure you're following. On physical disk, they are just bytes, but you might have some logical structure in your upper parts of your system that might be aware that your pages are lying in a tree format or a heap format, or it might be in a log format, or it might be in a what other formats are there? Yeah, main ones are these that you use a heap store based storage, you use a index based storage, which is actually a B tree, and you use a log based storage. So yeah, we'll just continue with that in the next class. And yeah, let's see. Thank you for watching.